log site in Hawaii. Brian, take it away. Thanks.
Hi, everyone. So I'm continuing in the Hawaii fieldwork theme. I'm going to talk about a study we've done recently looking at lava tubes on the Big Island of Hawaii. It's a collaboration with the RISE team of Survey, and I'd like to acknowledge my co-authors here. So what we did was study lava tubes using these three geophysical techniques. We did a magnetometer survey, a ground penetrating radar survey, and LiDAR surveys over and inside the lava tubes here. Here's a photo of one with Nick Schmer for scale. You can see they're quite large. They can be. They're quite spectacular inside. I'll show you some pictures of that in a moment. So the goals of this project were to measure the physical size of these tubes, what's the depth of the overburden, what are they like down there, and what are some of the textures that you see as well. We want to fit this into the geologic story of the site to see how we can learn more about the lava flows of the region, and also identify operational best practices that astronauts or rovers may do one day on other planets to use such techniques to better understand lava tubes on the ground. So lava tubes have been identified, we think, on the Moon and on Mars and perhaps elsewhere. And here's a rock image here, and you can see a lot of the linear collapse pits. And interestingly, in some sections, like the one at the bottom, we think we see areas that are not collapsed, which could be lava tubes. So what's a lava tube? Well, if you zoom in there and take a cross section, you can see a lava tube as a hollow cave. These form all the time on Earth. In Hawaii, for example, when a lava channel flows, the top starts to cool off and roof over, and that insulates the interior. The lava will continue to flow for quite some distance. Eventually, the source is exhausted and it drains out. You're left with the tube. So these lava tubes can exist for a long time, but they are rather weak on the surface. You can have collapses. You can have skylights, which are the holes in the lava tubes. These are also perhaps correlated with the number of collapse pits that Mark Robinson and others, for example, have seen on the Moon. So the question is, do these pits lead into lava tubes or not? If so, what's the extent of these tubes? So here's a nice photo inside one of our tubes. You can see the interesting textures on the ceiling there. And so why do we want to study lava tubes in the first place? I think there are three main motivations. One is geology. Because you're beneath the surface, you're not exposed to surface weathering processes, you get relatively pristine rocks. So if you're a geologist, you want to study the rocks and know that what's going on in the area. So I think this is a really good target for knowing what's going on in these planetary environments. The other one is biology, because again, you're shielded from the surface. There's a unique environment in these tubes. It's stable temperature, you're protected from radiation, maybe conditions favorable for water to be more stable, for example, on Mars. So if you're going to look for life, if you're an astrobiologist, lava tubes are a good place to do that as well. And finally, for those same reasons, lava tubes are very important for potential human habitation. So either for a habitat itself or just for sheltering during radiation events, a lava tube is a prime place to perhaps do that. So there we go. So this is our study area. It's an area on the northern slope of Mauna Loa. So here's context on the island. Nope, not working. So right about in the middle of the Big Island. And if you look closely, I'll show you some skylights there in a moment. This is about 2,500 meters elevation, and it's a very complex history, a lot of hoi and a'a flows from the past couple of hundred years. There's a lot of interesting volcanic features in this area, tumuli, skylights, scoria cones, etc. We have the high seas crews out there mapping these things every week. High Seas stands for Hawaii Space Exploration Analog and Simulation. That's a NASA-funded analog project that's been operating for the past 3 years here at this site. So it's unique in that we can have mission simulations run year-round. These crews can operate in isolation with relative autonomy, and there's a lot of interesting geology to go see. So in this case, you see a lot of skylights. If you zoom in, you can see them better on Google Earth, but remember that image of the moon that I showed you? This reminds you of that, perhaps, a number of skylights looking into a lava tube. We set out a survey grid of the area that we want to measure. We did our magnetometer, our ground-penetrating radar, and our LiDAR in this area. I'm going to focus on this northern end of it here in the talk today. Here's what it looks like zoomed in a little bit. There's not working. So there's a large skylight there. There's actually a collapse pit there as well where part of the tube gets pinched off, and we're going to show you that. So here's what the magnetometer looks like. You strap it on your back and you go. It's relatively easy to use. And I like that one person can do it. It's lightweight and it's relatively easy to process and get 3D maps in the field even. It's a little bit finicky, hard to use on the basalt surface here because it's magnetic rock itself. You have to be careful about that. And of course, being a potential field method, you have to model to understand and interpret your results, which is one complexity there. So that's the magnetometer survey. I'll show you some preliminary results from that. So we walked over that area there, and you can see the area in blue is actually the lava tube. So you can identify this lava tube underground. You can see where it is. You can also see here where it was collapsed, the area that's red at the upper right. So it's a good, quick way to survey what's down beneath the ground that you can't see with your eyes. There's the tube. So the next method, ground penetrating radar, is what we did. And here's the team over another section of the tube here. Note how rough the terrain is. Note all the blocky bits down there that have fallen in this skylight. So it's a very rough area. Imagine trying to do this with a rover, trying to do this with some other automated technique. It wouldn't be easy. So here we are on an part of the flow doing our survey. Now, because of this rough terrain, we're not able to drag the GPR or roll it on a cart, which are more common methods. So we had to pick it up and move it everywhere. And also note that it takes 3 or 4 people to do this because there's all the equipment to hold it. This was not designed especially for this type of work. It's meant for more benign environments. But here we are on one of the more smooth sections of Poyohoi doing the GPR. So I like that the GPR is a little bit easier to interpret in some ways than the magnetics, in that you're getting direct reflections, and you can see down and see see the different flow horizons, the stratigraphy that's beneath you. But because of the terrain, at least in this area, it's not a very practical method to use. I think if you're going to use GPR, you should fly it, you should roll it, somehow get it above the ground if you're in rough terrain like this. So here's one example of that. This is one of the deeper sections of the lava tube where I'm showing we can actually make out, if you take a cross section through there, you can actually make out that the tube, in this case, is about 6 meters down. So you have pretty good resolution on seeing that and picking out where the interesting features are and where you might want to go later. So the third technique, LiDAR, which is laser mapping, is very interesting. In this case, we have to go inside the tube. So it's not a non-invasive technique like the other two, but it's very high resolution. So here we are after clambering down into one of these pits and going in the tube, and you're treated to these wonderful views. And here's an example there. And you go in and set up your equipment on a tripod, make sure it's all working properly, and push a button. And it scans the area. You set up reflectors to control points to bring them back, and then you tie it all together in the end. So LiDAR is very nice because you can make these 3D maps, which you can geo-register and put into DIMS and other geographic context. Unlike the other methods, you have to enter the tube, you have to carry the equipment in there, and if you don't tie it in properly to the surface, your errors could propagate as you scan along. You have to be aware of that too. But I'll show you some image of that, some preliminary images, and you can see the lava tube down below, the green thing that's coming up at an angle, and you can see where it intersects the surface, and this is where one of the collapse pits came down and has filled in that part of the tube. You can take cross sections through that and look at a 2D section there, and you can study that and see what's going on. This is inside the tube, and you can see this is actually a range image showing basically, imagine you're standing in the tube looking along the profile or the axis of the tube, and this is what the walls and the floor look like. So it's a really nice way to see what's there without even having to be there. You could share this with somebody else, send it back to Earth, and give people a sense of what's going on. Now, a unique aspect of this project as well is that we're comparing to what the human crews are doing at the site. So we have human crews living year-round at the high seas site. The 4th mission is finishing up next month, which is a year-long mission. And we have them going out there mapping these features, including the lava tubes. This is one of the examples of the sort of maps that they can create. They go along and they measure and sketch out the cross sections at intervals along the tube. And they had an artist on this crew, and they did a nice job, I think, sketching out what it looked like and some of the photos below. The crew, I should note, have to wear the mock spacesuits and be encumbered with the bulk that the spacesuits bring. And so that sort of tempers what they're able to do. So what are some lessons learned from this project? I think having the crews on site is a really unique opportunity in this case, because we can go and we can test these ideas in the field. We can see what works, what doesn't work, how would we change the interfaces for either astronauts or robots to do later. In fact, how do we find who should do what in the future? Should people be doing ground penetrating radar surveys, or should we just do all that from orbit, for example, or have rovers do all of that? So this is the sort of thing I think we need to go to the field, ground truth these measurements, and work it out before we go up there. So here's Jack Smith doing some geophysics on the moon. Now, I can recommend magnetics for surveys of these lava tubes, definitely. I cannot recommend GPR on this type of terrain. So that's one of the preliminary results from this project. And going forward, we're going to analyze this data further. We're going to get some more in-depth maps of these tubes and fit it into the larger picture of the site. And there are more missions coming at high seas. NASA's third grant starts in January there. So stay tuned for more. Thank you very much.
Open for questions?
Jim?
Very nice talks, Jim Head, Brown University. So the why did you not recommend GPR? Is it just because, yeah, why did you?
This is in an operational sense is why I said that. So I think, remember the blocky nature, the offloads we have in the area, even the Pahoehoe are so broken up in this region that I think at least at this site, I wouldn't recommend that sort of system unless you can deliver it in a smoother way. So if you could have some really burly rover with big wheels, or you're lucky enough to have a site where you could drag it, that would be great.
Yeah, I think a lot of the Maury sites, it's probably okay. We
agree.
use GPR in Antarctica and sublimation tilts, which are actually as bad as offloads, and we're able to do it with some effectiveness. And the Maury will be, I think, a lot better.
I agree. The Maury would be fine, I'm sure. Yeah.
Yeah, I guess I just want to echo that. The key point is on that terrain.
Yes,
that's
exactly.
Wicked compared to the moon. And in a lunar analog simulation, we did install a GPR unit on the lunar electric rover that the crew were using, and it worked perfectly over a period of nearly 28 days.
Yeah. If anyone has a rover they want to bring out and let us try it, we'd love to. We could put one on there. Thank you.
Any other questions?